Okay, somebody asked about a mechanism.
Yeah, I did.
Which one?
It was 17D.
B?
D.
D,
That's
David?
called, Is that the sp2 carbocation?
Very last one?
Yes, it is.
Very last one. Okay, this is on page 63, the very last mechanism. That's going to be all right. Let's see how this looks, guys. See if we can make use of this with ordinance.
Yeah, it looks fine.
It's kind of low. If it's not good, we'll do something else. But the projection. Well, look at there.
It's fine.
Right here? Okay, you have your work. But I've got it right here. It turns out it's perfect. Okay. So we got 3 hydroxy groups. We got acid. I see the starting material has 3 oxygens, yeah? The product only has 1. Looks like 2 oxygens have left. How do you make oxygen a leaving group? Because if it leaves you, it's a leaving group.
Okay.
I mean, typically, I don't know do any way other than what we've been calling a leaving group. We got acid, okay? I see these pi bonds. I mean, typically, leaving groups leave, if you make pi bonds, it sounds like elimination. Okay? I want to protonate an OH properly.
Yeah.
Very often under acidic conditions, okay? Now see, once you start reviewing, you can say things and sort of, okay, as we move forward. But here we go. Under acidic conditions, when you have an acid, usually the first thing you always do is want to protonate something. Okay? This is what this thing does. It protonates things. It's an acid. What do you want to protonate? Well, which OH? There's only 2 to protonate. You can these are the same, so either that one or that one, because that's the same as that.
Yeah.
Which one do you want to protonate?
Yeah.
The end. Okay, protonate it and then do what?
Then form a double bond. Have like a.
Yeah, by what mechanism? So let's protonate it.
Okay.
I assume you can protonate it, although that's
Yeah.
sometimes a bad assumption. I assume everybody can protonate an OH. Okay. If not, you need to look in the textbook. Well, if we protonate this guy and we get an H here, first of all, that's going to be a positive charge. We learned how to turn positive charge during test 1. Now, what do you want to do from here?
Rip it off. Make it fly off.
Make it ionize?
Yes. Like fly it off into space.
Okay, like this?
Yes.
Ionize, but look what you're going to form, though. What are we going to form? This is a nice board. I wish we had a... Listen to that squeak. What are we going to have here?
Carbocation.
What kind of cation? Okay, and what did we say about those? Bad.
So it's better to revolve one in the middle.
It's going to be better to do the one in the middle. Let's protonate the one in the middle. Now, protonation is equilibrium. They're all being protonated. Let's see how this bad boy erases.
Wow.
Okay, let's pretend I protonated this one and we got that far. First off, is this, if we eliminate it, we're going to do E1 or E2 with this reagent? E2 requires a strong base. Sulfuric acid is not a strong base. Okay, it's going to be E1, it's going to be carbocation. But where do you want to make the carbocation? Not there, here. Protonate, ionize there, what do we get? We get that. These electrons breaking away, okay. It needs to be some precision with the arrows. I'm quite lenient, but when they just do like this, not good. These electrons are moving onto the oxygen. And we made water, and the O now has 2 lone pairs. There's the cation we can form. All right? Now what can we do now?
Have to
I could maybe make a bond here, but we're not looking to make a 3-member ring.
form the alkene.
Form the alkene. We do have H's here.
Yes.
Water or bisulfate, any one you want to use. And I'm not drawing this out, but these electrons, I'm not showing them, take the H. These electrons can move in here, and that would give... Now why those? Why not these? Well, that's symmetrical. Either way, it's the same thing. We get that. Oh, there's no H here. Just put that double bond in and we reformed our acid catalyst. So we just dehydrated this thing. We lost water and there we go.
Yeah.
That's not the product though.
Wouldn't there be
We just put the double bond in here with the second step of an E1. There it is. It's the second step of an E1. Everybody, yeah?
Yes.
Ionization is the first step. We first had to we had to do the protonation. That's an activate, that's a pre. Okay, we're basically doing E1. We eliminated one oxygen. Okay, what do you want to do now? We can now protonate another one. Where do you want to make the cation again? Because we can protonate and ionize, but you can't do a E2 elimination. You don't have a strong base. And there's no substitution here. This is elimination chemistry.
So
You want to protonate that,
No,
and then ionize and make cation there?
No, other one.
No, you don't want to make cation on sp2 carbon. You want to make? Can you make cation here?
Yes.
Now, it looks like it'd be primary, but is it really primary?
No.
It's resonated.
It's got resonance, so let's get there. These electrons, I'll do it stepwise here, and we get boom, boom, boom. By the way, that's an enol. Remember enols? We got this here, all right? Now we can ionize. These electrons break away and move on to oxygen. What's here now? Carbocation, we lost water plus H2O. We got an oxygen. The oxygen now has two lone pairs because these two electrons move on to oxygen. Is that just primary or is it better than primary?
Better than
Better than primary. Let's consider resonance. Maybe resonance will help us get to where we want to go. If not, it's okay. But there is resonance here, right?
Yes.
Windshield wiper. Move those over here. Resonance, double-headed arrow to illustrate that we're going to show a resonance structure, and that's going to look like. Is that it?
Yes. Can't you resonate it again?
You actually can, yes. But at this point, let's step back and look at what do we. It's actually flipped around. Because we removed the oxygen on one side where this shows it on the other side. But yeah, we can do resonance again. These electrons move in. What does that do?
Positive charge oxygen.
Double bond to oxygen. We didn't do anything with the H. It's still there. I'm fixing to lose it, so I'm going to draw that out as a bond. One lone pair, that's a plus charge. Those are all resonance structures.
Yeah.
Okay, are we close to the final product?
Yes.
Now, that's a carbon with an H drawn in. That's an aldehyde. I like to draw my H's in there. But if it wasn't there, just ignore it. What do we need to do to get there?
Proton.
Just remove the H. What can take it? Well, what was here? HSO4 minus. There's lone pairs there. The electrons take the H. This moves here. And that's going to give that with two lone pairs on the oxygen. There's an H there. You can draw it in if you want. Actually, you don't have to. I mean, if you don't draw it in, I know it's there. Because if there's no charge there, there's got to be an H. Can y'all see this board? Everybody? Where did you get hung up on this one?
So I basically made a mistake of taking one of the ones on the end, and then
You made a primary cation.
yeah, and then I made like a. Basically, I was ripping off an sp2 carbon. Did we rip it off? Did we? I know in the lab we like formed an sp2 carbon, which we then formed a cation on. But
We didn't form a cation on sp2 carbon. be the double E2 elimination?
Yeah.
Yeah, see, I kind of hate that lab because it makes you do bad things.
Okay. So that's bad.
See, I'd rather tell you never do any See, sometimes I tell you like blanket statements that hold true 99% of the time.
Okay.
We just happen to see that 1%.
Okay.
But we didn't make a cation on sp2 part. We eliminated a leaving group that was on it. It was
Yeah.
never a cation.
No.
It was a concerted E2. Questions?
Yeah, could you move like electrons from the oxygen to carbocation on the first part?
Tell me again.
Move electrons from the oxygen to like the carbocation.
You mean do this?
Down and then move like forming a double bond between the oxygen and the carbon, and then
Read this?
yeah.
And kick the H over at the same time? No. I mean, what are we doing there?
Yeah, could you do a hydride shift and then,
You want to do a hydride shift and not take the H, but just shift it over?
do the hydride shift and then do the resonance structure?
Okay. I mean, there may be another mechanism. Let's do a hydride shift. Not have something take the H, but shift it over.
Yeah.
I'm going to erase this, I think. What would that give? We'd have one H there, and that's a cation. And now the H is over here.
Yeah.
Basically, if you don't draw H's, it's going to look like that now.
Yeah. And then do a resonance
Yeah.
structure.
And then do resonance here.
Yeah.
Get that? All this is sound mechanistic electron movement, but how does this get us? How can we get where we need to go? What do you want to do next?
Remove the H from the.
Oh, okay. I'm seeing it now. We're going to get the aldehyde here, and then you're going to dehydrate. Yeah, you can do it, but still you're going to have to form a primary cation. I mean, we can have the HSO4 minus, take this H, these electrons stay behind, and that's going to give the aldehyde. There's an H there, that's the aldehyde.
Yeah.
Now we just need to put a double bond here. You're going to do that by protonating this,
Yes.
and then what?
And then doing E1.
Then ionizing. When you ionize, what are you going to make? Primary. Oh, I lost. No. Yeah, it's right. It's primary carbon. And then you could take the H, the electrons move in, and get your pi bond. Well, that theoretically, mechanistically works. It's just you're proposing to make the primary cation. First way, we never had a primary cation. That's a case where you would have got a lot of credit. Moving arrows correctly, having charges. I just would have had a cutoff for primary cation. Now, sometimes when we get to organic 2, there'll be mechanisms where you can do it many ways and they'll all be right. Or basically, unless we said it, it's definitely this way. Okay. Had you already worked that out, or did you just see that?
Yeah, no, I did that.
You saw it right there? Other questions? Question?
14B.
14B? I reckon I'll show it up top there. 14B. Maybe I can pull it down. Which one? Is that it?
Next one down.
Is that A?
That's a.
Right there? Which would be the reaction of choice?
Right one.
Y'all got it there on your paper. I'll make it so I can see it on the board. What's the best way to make the compound in the box?
Left one.
Looks like we're, in both cases, we're doing E2 elimination.
Yeah.
Elimination, strong base, E2.
The left.
This is not Carroll, there's no stereochemistry.
Yep.
Not really, because it has another problem. I think that has a problem over there. Let's see. Is this going to be regioselective? If you do this, is that going to be the only product?
It can make, yes.
Well,
There'll be another
yeah,
product, but
yeah.
in small quantities.
This is Satesef. You can also make Hoffman where the double bond would be there.
Right.
It's really bad.
Okay? That is going to be a major product with this base. How many products are possible over here?
Two.
Also two. You can put double bond there or there.
Hoffman's better. Let's not think it's better.
Both cases, I see two products, one Hoffman, one Satesef. I just figured out which one I like better. In terms of stereochemistry, you're asking?
Depending on where that chemical is in relation to that bromine.
Yeah, like if this is bolded and that's bolded, or if this is dashed, that means the H is bolded and it's not going to eliminate there. If it was dashed, this definitely would be. Okay. Yeah. Now see, some of these questions I make up, some of them I kind of take off the internet or so out there. Because I want you to see all types of questions and we can struggle a little bit with them. I just saw something. We're looking for this to do an E2. Could it do a substitution?
Yes.
Yeah. You just be E2 and SN2. Both possible. How about over here? E2, is SN2 possible?
No.
E2 only. For the E2, they both give two possible products. I do see the stereochemical thing, but I think what makes that one worse is you could get substitution there because it's on secondary. Okay. Now again, some of these questions in the workbook's homework, I may not put on the test because they're a little bit, maybe a wee ambiguous, a little wee difficult. We use it as a learning exercise and learn things from it. Okay.
For number 13, would that be a geotolerant?
Let's see. Was there anything else about this one?
Anybody? So I have a question. So the one on the left, the Hoffman product is like less stable than the one on the right? Because like one of them, it's a di-substituted alkene, the other one's like a tri-substituted alkene.
Yeah.
Does that play a role into like Hoffman and Zatesef being produced? Like the ratio of them?
It could.
Okay.
This question, I think the other one in this series is better.
Yeah. Okay.
I think this one is a little bit too ambiguous. I think the main point I want to make is look at the, did you recognize that one could do SN2 but this one couldn't? So if you want to do elimination, If you only want to do elimination, which one would you use? That one. So that's sort of the major take home. The other is sort of a little bit vague. Let's look at the other one. Which was it? One below or above it?
Above it.
Which one of these is best? We have the same start material, we just have different reagents here. Which reagent would you rather use? Right. See, I think this one's pretty straightforward. You'd rather use this, why?
It's easier.
You wanted to do only E2. Okay? This is not so bulky. It might just also do an SN2. That bulkiness is going to inhibit the substitution. And maybe not make it totally inhibited, but it's certainly going to reduce the possibility. That one is more straightforward. So there's a question about Diels-Alder, which number?
Number
13? Is that it?
Yeah. In the box, in the brackets, is that a Diels-Alder product? Is that what you're asking? Yes.
Yeah, it is.
Okay.
I mean, all you got here is really alkenes. Alkenes react with electrophile. There's no electrophile, traditional electrophile there. Lots of pi bonds, Diels-Alder. And what? Well, here, this is a benzene ring, and in this class, never do anything with benzene ring. All right? Once we do stuff, we'll learn. So if you ignore that, what does this look like? It's like butadiene. This is symmetrical, and so that right there would be just an alkene. So that'd be 4 plus 2. You can do it either side. So there's your 4 plus 2. Boom, boom, boom. So let's show the product if you haven't already. And then from there, this is a way to get to making like estrogens. I'm going to draw it here so it's a little bit bigger. Let's see, I'm going to draw 4 plus 2 makes what? 6. I'm going to make the 6 first. And the double bond is going to be here. Well, now that I do that, it looks like it might be easier. Draw the ring first, so I can see where I'm at. And that 6 is there. That's the 4, 5, 6. So we just made that bond and that bond. Where's the double bond, the new double bond?
Left side.
Right there. Then this is, that's 1, 2, 3, 4, 5, and 6.
Yeah.
That's 5 and 6.
Yeah.
Now 6 has this. These are cis. How do we want to draw these?
Back, forward.
Either way, but the same. Because now these are tetrahedral. So we can have them sort of like this.
That's not already implied with that small of a ring.
It's already implied with what?
It's not already implied with that small of a ring.
Probably, but I think we need to, I think it's, yeah, it's almost redundant, but it's just good to show it. We just made this 6-membered ring, making the bonds I highlighted. It's one equivalent of each. Now, if you had 2 equivalents of this, you would do it over here also with another equivalent, and you would build a molecule where you had one of these and two of those. Because that could react again in Diels-Alder. This theoretically could too, but it's quite crowded. Diels-Alders, if you get too much sterics, they don't work. But if you look up estrogen, you'll see the sort of four rings like this. There's more to go. Typically, this is removed, and then like this methyl's removed, and you get like an OH. Like you've heard of estradiol, diol on the end, OH. You know, this would be one OH here, and you'd probably have another OH up here or something, maybe. Questions?
Can you do question 10?
10B? Next question, I love it if it came from one of the back 2 rows. (10B), is that correct? 10B? The HCl salt. Let's see if this will show up at all. The HCl salt of ephedrine has a specific rotation of -34. What would you predict for the specific, what's it say, specific rotation of the HCl salt of pseudoephedrine? Here's ephedrine, here's pseudoephedrine. What's the relation between the two?
Guys, there. Ephemeris.
I only see one change. There's 2 chiral carbons, only one is changed. If you want enantiomers, you have to change them all. Only one is changed, so it's epimer, that's a type of diastereomers. So, if one has a specific rotation of -34, what's the other one going to have? That'd be the enantiomer, right?
I have no idea.
I have no idea. The answer is we have no idea, unless you look it up somewhere. Because the rotation of diastereomers is totally unrelated. Just like melting points. You remember the melting point of the 2 dibromide diastereomers, meso and DL? They were like 100 degrees different. It's just, who knows what it's going to be. But the enantiomer would be +34. Right? Is that why you were wondering? You were kind of confused? What's the answer?
Yeah.
Well, you're right. What's the? I don't know the answer. But that's the answer. We don't know. Okay.
Number 15.
I can't hear.
15.
15. Synthesis. The synthesis on the chest was in the workbook, right? Cymbalta. It had a different ring, but that was inconsequential. Supply reagent or sequence that would give the following conversions. How would you convert this to? Let's do the easiest one first, just to get us started. That would be maybe the easiest. Perhaps the bottom is the easiest. How would you go from that to this? KOT butyl. Turk butoxide, a sterically hindered alkoxide base. Yeah, because what type of mechanism do you want to do?
You do Hoffman.
What mechanism gives Hoffman?
Big spaces.
E2. Does E1 give Hoffman?
No.
No, E1 gives most substituted. He gives, that's going to be Seiza. You want to do Hoffman here. What promotes Hoffman? You need a big old bulky base that can't take the most accessible, or the, see this H here is kind of hidden to put the double bond in there. That one out there is more accessible, bigger base is going to say, I can't get there, I'm going to take this one. Yeah, something like that. Steer clear of the base, E2 elimination. How about the one in the middle? One step to get to product. Looks like we've replaced the bromine with a, what do you call that group?
Methoxide?
Not a hydroxy, but a methoxy. Meth, or ethoxy, or propoxy, or methoxy. It's a substitution, obviously, yeah. Do you want to do SN1 or SN2? Why SN2? Because we need inversion, only inversion. SN1 will give racemic. Most. That's what we said, most. There's a question in the workbook that talks about how it's not exactly 50-50. Some folks just ignore that. But we definitely, it looks like we want inversion. We want to do SN2. So what reagent do you want to use?
Silver methoxide?
Uh-huh.
Oh,
Oh, Miak.
that's
What is Miak? Now, nobody ever calls it Miak. I just have kind of a history. Okay, I have a question with that. Not a question, but a history with this, so it's kind of funny to me. But I won't share it. That's potassium, right? And so this is ionic. What's the charge of potassium? Plus. So what's the minus? Yeah, and then what's the Me? CH3? Yeah, I mean that is CH3, O minus, potassium plus. I mean, however you want to show it. And so you want that to do what? These electrons to do what? Can you do SN2 on that substrate? Whoa. Yeah. Not as good as primary. That's the only one-step approach I know. If you tried heating it, what if you just tried heating it in methanol? That is the neutral version of this.
You get the SN1.
Will that do SN2?
No.
Yeah, methanol is not good for SN2. You need a strong nucleophile. You probably do SN1 or E1. So you're going to make carbocation. If you make carbocation on this carbon here, is it going to rearrange?
Yes.
Probably. The H will move over and get a nice cation here that's doubly stabilized by 2 benzene groups. So if you try to do SN1, it's probably going to rearrange on you. I may have just given away the, I did? I gave away the top one? Yeah. Okay. Well, good. So what reagent do you want to use back there? Reagent there?
Hydroxide? Hydroxide. That's sodium hydroxide.
What reagent do you want to use? MEOH? That oxygen has a methyl on it. This one doesn't.
You're right.
H2O and heat. Well, that's the old thing. Does any heat give an elimination? If you actually look at like when diethyl ether was first made back in the 1800s, it was been used as an anesthetic. The elimination product occurs at like 180, but if you do it at 140, you get substitution. So does it make sense that higher gives elimination? But you still have to do it at 140. So you see, I just kind of know that you're going to probably have to do some heat to get this to ionize. What's another way, instead of using heat, that we might could promote the ionization? Polar solvent would definitely help. What's another way? Yeah, like silver what? Silver nitrate. Silver sulfate probably okay.
Silver nitrate promote elimination of BR instead of substitution.
Nitrate is not a good base. Nitrate would just be a spectator ion, usually.
What's up?
Nitrate is the conjugate base of nitric acid.
Strong acid, so it's very weak.
Strong acid, that's the conjugate base, is very weak. Question?
What do you think of silver fluoride? Or is that like, it's not
Silver fluoride?
Yeah, it's not even ionized.
Silver fluoride won't dissolve in water.
Okay.
It goes back to your Gen Chem solubility rules.
Yeah.
So, what'd you learn about solubility of nitrates in Gen Chem?
They're always like,
Yeah, see, nitrates are always soluble just about. That's why silver nitrate is a good one. That's a very practical thing that is often never mentioned, but, and that's why you learn solubility rules, so then you can understand that, but I wish we did more of that. To me, it sort of makes it relevant. Why silver nitrate? Did we get everything answered here? Any questions? Isn't there a country song about the back road?
There's a lot of times. Well, you covered.
I'd love to do that. Number 12 on this page, up there?
Yeah.
It looks like a, is that it?
Yeah.
HBr, it's an acid, but it can also be a reactive. We did HBr reaction, addition of HBr, alkenes. What do you want to call this compound? Main functional group is there. Diene, yeah. This is like diene chemistry. And then at this point, you kind of go, okay, heat, diene chemistry. Yeah, cold versus heat. What does heat give? Most stable. A lot of books just say you get to 1,4, but that's not always right. Sometimes the 1,2 is actually the most stable. We got to figure out where we're going to make cation. It's either going to be in the middle because it's going to be resonance stabilized. What if we make it here? H plus is alkene chemistry. Attack here. That's actually pretty nice because the writing is blocked, free writing space. It's like you don't have to. We're going to get. Is that right, Dustin? Resonance stabilized, then we do resonance, windshield wiper up, resonance arrow. Hold on, let's do the resonance. Is that all right for this kind of? This is secondary. This is what? Tertiary. Okay.
of the alkene.
You mean of the resonance structures? Let's get the others up here first and then let's look at them. Instead, what if we react this pi bond? Well, we're going to make cation on the left, correct? So it'd be resonance stabilized. That would give plus there. UH here, swung out, then this can do resonance. Pinch down, cation there. There you go. There's your other resonance stabilized cation. It has characteristics of tertiary and primary. Would you rather have tertiary primary or tertiary secondary? Tertiary secondary. So at this point, we're going to get rid of this. So now we said it's going to start out like this. Now that it starts out like this, the bromine, the Br minus, can either end up added to this cation or that one. Heat gives which product? Most stable alkene. Which is it going to be? With bromine here or bromine there? But bromine's here, we got a tetrasubstituted alkene. If bromine's there, this is just a trisubstituted alkene. Your alkene rules is what is the most important here. Br, which we already had, here. We don't show cation attacking Br, et cetera, et cetera. And when it does, what do we get? We get final product that looks like well, I didn't redraw it here. There's an H there. There's actually 3 there on the end. There's your final product, right? It's a tetrasubstituted alkene. It's got 4 carbon substituents. Let's talk about stereochemistry. I wanted to ask, though, is it 1,2 product or 1,4? Is that a 1,2 product or 1,4? This is a 1,2 product. Where's the new H in this compound? It's right there. I drew it in. If I drew it in, it'd still be there. There's the new H. The Br is there, so it's 1,2. Right? This is a case where the most stable alkene is actually the 1,2 product. Okay, here's a question for you. How many stereoisomers are possible for this product?
1. Well, actually, that's a carbon. So 2.
2 total. How many total? The answer is 2 total.
Yeah. 1 power touch.
You got the R and S versions right here. That's racemic. Because is that alkene stereogenic? No, it cannot be essentially like cis, or you can't have the 2 bonds of the ring going opposite. You couldn't make a 6-membered ring. You have to get up to like 8, 9, usually like 10 or 12 to be able to have a type. So there's 2. Which one are you going to get of the 2? It'll be racemic, because how do you attack cations?
Both sides.
Both sides. Did that answer that? Question?
Can you do 17A?
17A. phenylimineene. Is that it? It's like we have to make a 6-membered ring. The oxygen's gone. I make oxygen a good leaving group. Do we have acid available? Uh-huh.
And yeah,
We can protonate the oxygen. We can also essentially protonate the alkene by doing alkene chemistry, with the alkene attacking the H. It's also called protonation of the alkene. There you're not protonating a lone pair, your pi bond is reacting. I see this carbon here with this 2 methyls. That almost looks like it's that right there. And so we sort of end up with a double bond here maybe instead of there. Do what?
The double bond on the top. Sorry.
Yeah, it's like it's kind of moved over here maybe. Okay. I'm not seeing it quite yet, but that's okay. You don't have to see the whole thing. Just take stock of what we want to do. What's your options? I'm dying to protonate the OH.
yeah.
Let's see where that leads us. Because I could then ionize. And would that be primary cation? Would it be resonance? Okay, so I'm going to try this out. Let's protonate that. Yeah? Instead of redrying that, can I just show the result of that step? Protonate. I mean, after that, there's no nucleophile here of the water. If you kick that off with water, you don't get anything new. The only thing you can do here is really ionize. If we ionize, what do we get? Somebody say cation, or did that come from the sky? It sounded like it just came from the wind. Cation. Looks like primary, but it's really resonance stabilized, yeah? I don't know if we need to consider resonance or not, but I'm going to draw on the board and take a look at it. Resonance would look like this. That's resonance. Can we make a ring here? Six-membered ring. 1, 2, 3, 4, 5. 1, 2, 3, 4. I envision the pi bond attacking up here. Pi bond can attack an H plus. But 1, 2, 3, 4, 5. That's going to be a 5-membered ring. Maybe come back here. I mean, this cation is a blend of these two. That doesn't mean we can't work with this here. You can work with any resonance structure. This is a stabilizing feature. 1, 2, 3, 4, 5. We want that carbon to bond there for 6-membered ring. Is there any way to get that carbon to bond? It's pi bonded. These pi electrons can, instead of being down, the top carbon is what we want to bond there. the top carbon, like my shoulder, can it break away and go bond? Yeah, that's what we always do, alkene. It breaks away down here, and goes bond, and that looks like a long way away, but it's like this. Can my hands clap? Well, yeah, I could do, the bonds can come together. What does this give? Again, this is pulling away from down here. Top carbon's bonding. I'm going to erase the resonance structure. You have that. Also this. This really needs to become, it's drawn here as sort of E. This can change because I've already erased the resonance structure. But if you look at the resonance structure, when it was here, this could rotate. You can do that, and you wouldn't have to account for that. But that really needs to be drawn down like that. Then it'll look a lot friendlier. This attacks there, and what does that give? It gives a 6-membered ring, double bond there. Which bond did we just make? That one? I think so. We're here, we have this, 2 carbons. Let me redraw it again. Used to be here, but instead this came up and made bond. So now it's bonded there, but what is here? Carbocation. Now this thing is planar. We can flip it around. I could redraw this. That's the same exact thing. I really didn't need to redraw it. But here it's over here. Okay? What do we need to do to get home? We're only one step away. What do we need to do? You got to take an H and put it in the double bond. There's 2 H's here. There were originally 3. We want to use water. Well, we formed water. The water we formed, there's also plenty of water around probably. Take the H, these electrons move in. Electrons move in to make the pi bond, and what do we reform? H3O plus. This is really catalyst. We eliminate water, but we also do a ring formation. So, how do we do? Was anybody thinking something else? Do what?
There's still more to it.
You want to make the pining? Okay. Pining, it looks a little interesting there. I'm going to erase this if there's no questions. So the exam is when? Let's talk about that before we end up. Tuesday at
8 p.m.
8 p.m. All right.
Good time.
We'll have section C be in the room next door. Then the other small lab, I think, is who has lab on Wednesday afternoon with Dr. Armando? D? E. E is Wednesday. Dr. Armando, is there E folks here? Okay, how about E also being next door? C as in cat, and E as in elephant. Elephant and the cat. E and C next door. Would that be good? That'll be Those two should fit. I'm gonna write that down here, E and C. E, C. Anything else about the final exam? How do we make limonene pinene? Probably shouldn't have erased that cation.
Yeah, you're gonna need it.
I think we're going to just go right back to it.
Yep.
Protonate the bottom alkene, make carbocation where?
Sorry.
Left or right?
Left.
Yeah. And I think this gets us right back to what we erased before we deprotonated and formed it. Yeah? What can this do?
Alkene can attack.
Alkene attack the cation?
Yeah.
See, this looks a little like bond strain here. One thing I keep in mind, that's tetrahedral. So that's not planar. This is sort of coming out of the board. And so the alkene is here, and that thing is sort of, it's not straight away. It's sort of a little bit, so the bond angle is a little bit there, and that alkene apparently can do it because there's your structure. The alkene electrons can somehow bond to that. We can sort of show it. It ain't gonna look pretty. When these react, we're gonna leave cation on left or right.
Right.
So I'm gonna break away from that and sort of have a bond there. How can I show this? I'm gonna draw the 6-membered ring back there. Cation is gonna be there. All right, it's gonna be ugly. I'm gonna draw it. Like that.
Holding it up.
This is like, there's your ring with a 1-carbon bridge, and the carbon has 2 methyls. Now I could redraw that so that bond's not as long, because in real life it's not. I really need to 3D. But I could draw it something like this. There's the carbon with the 2 methyls, and it's bonded there. Now I can make the methyls so big that they sort of extrude over that. So we still have cation here.
Attack
How
protons.
do you get the final?
Protons.
Well, we got 2 H's here, and you only got 1 there. So the water, take an H, electrons move in, but the double bond in there. And that's a known structure. I mean, it's fascinating. It's interesting. It's got this bridge, and it looks like, how does that happen? Well, if you make a model of it, you can see it. All the bond angles are probably 1 and 9.5, pretty much. It's just, it's more of a 3D structure. I was wondering, they can't change the syllabus or anything, but let me ask you if, for the quizzes, a couple of people asked about the quizzes. Would y'all like to consider doing something, for quizzes differently than the syllabus states?
What is the syllabus?
Huh?
That your lowest grade is replaced with 10% of your lowest test grade.
No, we do that. I mean, that's what the syllabus says.
Is that replacing your lowest quiz grade or replacing your quiz grade entirely?
No, one low quiz grade. That's what it states. So if you made 100 on all 3 tests, and you made like 5s on all the quizzes, one of the 5s would be replaced with 10% of the 100. So one of the 5s gets replaced with 10.
10% or a 10 out of 10.
What were you proposing?
Yeah, good question. Something like, we had 3 quizzes.
Yeah.
Yeah. Something like if you had, we'll make each quiz a 10 that you took. If you missed a quiz, and that's still 0, but if you took 3 quizzes, that'd be 3 10s.
Yes.
If you only took 2 quizzes, and that'd only be 2 10s. Y'all okay with that?
Yes. Absolutely.
Okay? All right. Just for you guys who are here. That'll be our secret.
Okay.
Okay.
The way it proves we're here.
I know you're here. All right. What's next? We got video proof too. So if you've spoken, if you've asked a question, then we'll have proof that you were here. But if you haven't asked a question, then you can't be liable for that.
Nicholas Forrester.
You know I'm kidding. I have to do it for everybody. Okay.
Extra credit to people that were here the day before Thanksgiving, though.
Yeah.
There were only 39 of us, just saying.
I can't give extra credit for attending class. I guarantee if you look at the grades of those who didn't attend, that probably they suffered not attending. Maybe not, but in general, yes. Your good efforts are usually rewarded. Next question. 17B. The next mechanism? Yeah, typically the mechanisms are ones we want to look at. That one there? We got an old alkyne. I know we only had 3 quizzes, and it's hard to mess up on when you grade kind of suffers. The other 3 we didn't grade, right? Okay. Well, it looks like similar chemistry. We got OH, we got pi bonds. What do you want to do first? The product has a ketone and a new ring. I'm not sure if the oxygen is really left. I mean, star material has an oxygen, the product goes 2. But it's not certain that it's left. You could maybe leave and come back. What do you want to do first? Anybody? Coordinate the OH?
Yeah.
We can see where that takes us.
I would approach the alkyne first.
Yeah, I'm going to coordinate the OH only because that's the first suggestion. I'm not quite sure. Why would you coordinate the OH?
There's nothing else to do with it. Well, I guess the alkene, but that's bad.
Yeah, it's still there, but it's not on a 6-membered ring carbon though. Here's a 6-membered ring, and there's not an oxygen still bonded to that. You see? So to me, it's like it's somehow maybe it left and came back. No coming back? Again, we can see, if it doesn't take us, if we're going down the wrong road, we can backtrack. Okay, we know how to do that. It's going to be drawing. I'm just going to show it prodated. What do you want to do after that, possibly?
Alkene attack.
Attack what?
Oh no, we'll rip the water off and then have the alkene attack.
You want to rip it off?
Yeah.
Okay. That's slang for ionize?
Yes.
Here, boom, boom, boom. Cation there. Oh, I'm seeing a five-membered ring. I'm seeing a five-membered ring, yeah?
Yes.
This carbon bond's here. How could that happen? The electrons hinge over.
Is that strange that it's 180 degrees?
What's 180?
The alkene.
Well, you're right. The way I've got it drawn, that should be linear. I mean, if you want to draw it linear, yeah.
No, I was asking, like, is that like strained? Because it's like literally it's like going back, right? I guess a hexagon is like complicated.
Well, now it's linear,
Oh.
but the electrons can just break away
Okay.
and fall over. Hold on, we're making 1, 2, 3, 4. No, we want that carbon to bond for the five-membered ring. Well, that's what I'm doing. I'm liking this. Pull down, breaking away from there. So that carbon bonded. There's our new bond. This carbon still has a double bond, but now it's trigonoplanar, so I'm going to draw it with a 120-degree bond angle. And this has a methyl. Where's the cation? If that's A, B, C, D.
B.
A, B, C.
B.
I want this to break away in the bottom carbon's bonding, leaving B a cation, right?
Yeah.
Yeah, because look, B has no H. There's no H there, so there's your plus charge. Now we got a five-membered ring, double bond. That double bond apparently just never did anything. Now this carbon out here, there's your five. Carbon, what do we need to bond here?
Water.
And oxygen needs to bond there in the form of what?
Water.
These electrons here. I'm going to draw it like this. Okay, stereochemistry is not going to matter. I'm going to draw the OH here. It's more than an OH. There's another H, and there's a lone pair, and there's a plus charge after water bonds. So now we have a one bond to oxygen to carbon. We've got to turn that into a double bond. I'm going to erase here. We got to get a double bond between here. We got to lose both of those H's to end up here. Now that has free rotation, so this could turn and the O can be down. What is this starting to look like? What chemistry? What's the donkey say? Eno. Okay. Doesn't say like Eno. Never heard of donkey? And look it up on the wiki. Is that what a donkey sounds like?
Yeah.
I'm sure it's only a little bit, but it's. Okay, what do you want to do next? Do what? Lose an H. What are we going to do? We got water. I mean, there's lots of water here. This is usually If you want to consider stoichiometrically, remember this water we eliminated? It's around somewhere.
We just attached
See what?
it. We just used it to put that.
Oh, you're right, we used it. So what can we take?
I mean, it's
Well, there's got to be a minus here. You can't just put an H3O plus. So maybe there's an HSO4 minus. But anytime you're using aqueous acid, there's plenty of water around because it's dilute aqueous acid. It's acid in water. So yes, I'm using another water molecule, but it's around. This can take an H. These electrons stay behind. And we're going to get the neutral structure. Which is that, and that is what? An ene,
All.
as an enol, okay, plus what? H3O plus. Now, are you seeing it? Enol, what do you call this form?
Ketone.
Ketone. What's the mechanism of going from the enol to the ketone?
Oreo.
Oreo, right?
Yes.
And what's the first, what does O mean?
On.
On.
On. Under acidic conditions, where do you want to put the proton on?
Water.
On the O? I would just take this back there. What needs a proton?
That one carbon.
That one there. It has none, but there's one there. We want to put the H on there. We got H plus. I mean, that supplies H plus. I've always just showed H plus. Is there any way to get H here? Yeah, it's alkene chemistry. This just breaks away. And where are we going to leave cation?
Tertiary.
Well, that'd be tertiary also.
Oh yeah.
We're actually going to leave it there
Resonance stabilized.
because it's resonance stabilized. So a new H is there. What's here? Cation. What does that allow us to do? What's after O in Oreo?
Resonance.
Resonance. Now we can move in the pi electrons, make the double bond, which we need to do. I'm going to erase half of this. And the H is still there. I'm going to draw this bond out now. That H is still there. I'm not going to draw it anymore. Double-headed resonance arrow. Now what do you want to do? O re
On.
off. We got to take this off. What do you want to take it off with?
At water.
Oh, water.
Another
Water.
one,
The thing that gave up the H plus, water. I drew the bond in so I could show the electrons moving on to the oxygen. That's a precision which I usually let slide. I'd rather you do that instead of having this. A lot of times you kind of do that. It's like this arrow is just not making sense. It's because you need to draw that bond out. Okay? You can draw it that long if you want. Take the H. These electrons move where? Onto the oxygen. So show it. Don't do like this. All right? Be forceful about it. They're moving there. Okay? And when we do that, what do we get?
The product.
Product.
There you go. I'm hoping that these looked a little intimidating. You had given them a try. You didn't quite make it. But now that you're seeing it, you're like, okay, it's making sense. Would you do something else here? Where did you get caught up at? What looked odd? Next question. The other mechanism? See?
Yeah.
See, it's a little bit unique, just in terms of what it does, but it's not really unique in terms of mechanism. 1-bromobutane. You remember back when you didn't know what 1-bromobutane was? Okay? Do you remember back when you didn't know what a carbocation was? Okay, that, we got this reagent. What is TA?
Triethylamine.
Yeah, triethylamine. What's it often used for? Elimination, because even though it's neutral, it's strong enough to do an elimination. It's just strictly under a strong base. We got this interesting guy. It's called an N-oxide. What do we have over here? We have 4 carbons. Seems like the bromine is gone, and on the N carbon is now bonded to an O, but it's double bonded to an O. Everybody agree we got to replace the bromine with an oxygen?
Yes.
Do we have an oxygen on the board? Is it in the form of a good nucleophile that can displace the bromine? I mean, it's minus. It's like an alkoxide. Yeah. What if we do? Okay, this doesn't look like backside attack, but it also isn't three-dimensional. If you'd rather me come in over here, either way, what does this give? One, two, three, four. Now bonded to that carbon is oxygen, and that's bonded to an N that has the ring with pi bonds. The nitrogen is plus. What's the charge of the oxygen here? 1 lone pair is now bonded to that carbon. The other 2 lone pairs are there. It's what? It's neutral. That's plus. I mean, everything is net neutral. We have to have something to balance this charge. What's the minus?
Br.
Yeah, Br minus, the leaving group. That's just a good old SN2, right? Okay. Now this is an aldehyde. That carbon only has 1 H. I like to draw them in. How many H's on the carbon there? 2. What do we need to do? We need to put the double bond in here to O, remove an H. Looks like an elimination. Remove an H. Does the O have a leaving group on it?
Yes.
Nitrogen is a positive nitrogen, a good leaving group? Can be. It's like a positive oxygen. Now that's not a carbon with a leaving group, it's an oxygen with a leaving group. That's kind of the twist. It's okay. Do we have a base that could, what type of elimination do you want to do? We got triethylamine, what do you want to do here? E2. What if this takes the H, these electrons move in, and these electrons, the leaving group leaves the oxygen. What does that give? Gives final product plus what? Plus the leaving group. This leaves, becomes a lone pair. Let's completely balance this out, show everything. Triethylamine is now bonded to what? An H. Thus, this has a charge. What's the charge? And what else is here? Br minus, which we formed over there already. This all together is a salt. That's a neutral byproduct, and that's a neutral organic. Well, that's organic too, but this is a unique way to make an aldehyde, all in one reaction. Triethylamine is very cheap. This is unique, but it's not highly uncommon. Mechanistically, though, does it seem pretty standard? Majority of the stuff we talked about with substitution elimination, everything was carbon, right? You could do some of those with other atoms. Like this was an oxygen involved with the elimination. Instead of an alkene, we made a carbonyl. On the other hand, I'll let you know this. A lot of the rules we talked about with carbon, you can't do that. For example, you can't do SN2 on a tertiary. A lot of these rules are just for carbon. And for example, if you go down to silicon and start doing silicon chemistry, some of the rules we've said don't apply. The main reason is because silicon, two big differences. Silicon has d orbitals, and also silicon is bigger